So we're going to be looking at type 1, type 2 error and power. You may recall we did those back in, I think, January, maybe early February, probably January. All right, so here's the thing. When we do a test of significance, we're going to make a decision. We're going to reject HO or fail to reject HO. We're going to make a choice between two competing claims. Since it's based on probability, there's a good chance that our decisions will be correct because we are going to be accepting, quite a lot of things probability-wise that are in our favor. But there still is a little bit of the probability that is not in our favor. So just because maybe we got a bad sample just by dumb luck, that may push us over into making the wrong decision. So one way to make a wrong decision is to commit a type 1 error. And you'll remember that. That's where HO is true, but you reject it, right? And there's a probability associated with that. It is your alpha. Alpha is that region in your curve where if you end up with your test statistics landing in that region, that's where you're going to reject. So it's the only place you are rejecting, and so it's the only place that you can reject and make an error doing it. So 0.05, that's the probability, if that's your alpha, of making a type 1 error. Another way to make an error is to commit a type 2 error. And remember, for type 1, that's where you reject HO when it's true. Well, a type 2 error is sort of the opposite. That's where you you accept HO when it's false, right? So a type 2 error is when you fail to reject HO when it isn't true. Another way to say it, or another way to think about it, is that you accept HO when it's false. So that's how I remember these things. Type 1, reject HO when it's true. Type 2 is accept HO when it's false. Now the probability of a type 2 error is beta, which is not something that you get to pick. It's based on some kind of alternative value for HO, because look, if HO is not true, then there's got to be some HO out there that is. So the reality you think you're in is really not correct. There's some other reality that's centered at a different HO value that is true. And whatever that alternative is that you pick determines the probability of a type 2 error. We used to have to calculate it. Now we don't. Just kind of know where it comes from. Now, you'll recall that a type 2 error is worse than a type 1 error. A type 1 error, your original conjecture is true. You don't think it is. So you go about trying to see about fixing that situation. You find out the situation was fine, and you just go back to your regular life. A type 2 error is when the world you think is correct isn't, so you're not doing anything about it. So if you have a power plant, I always use this example, and you think that it's running at correct settings when in fact it's spiraling out of control, you're just going to go sit down and eat donuts thinking everything is fine while your plant is melting down. So a type 2 error is worse than type 1. Type 1 error is not great, but type 2 error is worse. That brings us to the third item, which is power of a test. So the power of a test is a measure of doing the right thing when you make a decision. And doing the right thing when you make a decision in inference is to correctly reject HO when it's false. That if you can do that, then that's the whole point in testing. And if the chance of doing that is high, then that's actually the power. So in other words, power is the probability that you don't make a type 2 error, right? If it's the worst of the two, we want to make sure that we do reject HO when we're supposed to. So numerically, power equals 1 minus beta. All right, so let's just use the geometry to kind of make sense out of all this, this curve that I'm circling right here that's sort of up and to the left is the world we think we're in. It's centered at some conjectured value, and we set an alpha, and if we reject, that means our test statistic will fall in this little red spot, and that's the only place where we can reject HO, that this proportion is whatever we say it is, and make a mistake doing it, all right? But let's just say that this HO value just is not true. Well, that means that there's some other value for HO that is. Let's just pretend it's this. See how this is a conjectured parameter and this is actual parameter, all right? And so while you think you're in this world in the upper left, you're really in this world in the lower right. And this is your type 2 error, because these are the things that you're accepting in the first curve that you should be rejecting. So if you transpose this beta into this top curve, you would be accepting things, you know, right here, where you should be rejecting them, okay? So, and you can see that alpha and beta are tied together. You know, this shares where alpha starts to where beta ends, right? So if you opt for less of a type 1 error and move this line further to the right, that's going to also move this line further to the right and make your beta area bigger and the probability bigger. Now the power is on the other side. So if you make for a bigger beta region, you're going to make for a smaller power region. So you can see the linkage here, right? If alpha gets smaller, then beta gets bigger. If beta gets bigger, then power gets smaller, right? So on the other side of this, if alpha gets bigger, then beta gets smaller. And if beta gets smaller, power gets bigger. Now that's one way to improve the power of your test, is to accept a bigger probability of a type 1 error. To make this bigger, this region in the first curve, that'll make this region in the second curve smaller, and that'll increase your power. The other thing you can do, if you remember right, is to increase your sample size. Now you'll still keep this alpha, let's just pretend it's 0.05. That never changes. But as you increase sample size, your sampling distribution is going to grow. It's going to grow in the center and it's going to shrink in the tail, and that'll make beta get smaller. Smaller beta means more power. The only other thing you can do is to scoot this true value further to the right, so that this overlap portion or this beta portion shrinks, but that's kind of a finagle. I like the first two. To improve power, you can increase alpha or increase sample size. Occasionally they ask you that on the AP exam. All right, so finally, again, let's emphasize the relationship between these three things. All right, if you decrease alpha, you increase beta. If you increase beta, you decrease power. And it goes the other way too. So if you increase alpha, you decrease beta, and if you decrease beta, you increase power. Yep, that's kind of how it works. And there it is in words. So I think that's everything that I've got for your error analysis for inference. If you want, you know, a better presentation, you can go back to look at what I originally had done back in January. All those videos and all those notes are there. But I think this summary is probably going to be enough for just about everyone. So let's go to the examples. All right, let me go ahead and open those up. And the examples, if you look at Thursday's announcement, I'm going to put this exact set of problems. I believe I've got, let's see, do I have 4? I guess 5 of them. And what you can do if you want is just pause the video now, download that from the announcement, and work these things. And then come back on and see if you can, you know, match up, or you can sort of, you know, evaluate your own performance with this. So I'm going to just move ahead then and start out with number 1. So an environmental scientist wants to test the null hypothesis that an anti-pollution device for cars is not effective. All right, so let's just start out to get these things right. Let's just go ahead and write out HO and HA. So HO, and we'll just say device is not effective. I think I misspelled that. Get this off of here. All right, sorry about that. And let's just go ahead and put HA. And we'll just say device is effective. Okay, so under which of the following conditions would a type 1 error be committed? All right, let's kind of write out what that is. That's going to be to reject HO when it's true. All right, so we're going to just kind of say that that HO is true. So let's see, that'll allow us to go ahead and eliminate some choices. Scientist concludes concludes that the anti-pollution device is effective when it's actually not. All right, yeah, that's out. All right, because they're going to reject HO. Hold on just a second. All right, I'm so sorry about that. I was looking out my window and I was getting a delivery, so that kind of threw me off a little bit. So let's go back to here. I took off that A. All right, so we reject HO when it's true. So that essentially means that it is not effective, but we think it is. All right, so let's start out with this first one. The scientist concludes that the anti-pollution device is effective when it actually is not. All right, okay, if you reject HO, then you're believing that the device is effective, but it never was effective, so it matches up to A. The scientist concludes that the anti-pollution device is effective, and we think it is, when it actually is not. So A would be your correct answer. You can run through all the other choices, but I think it's pretty clear that that is correct. All right, so there's your first one. All right, so number 2, an advertisement claims hair builder cures male pattern baldness. Your father wouldn't mind more hair and is evaluating the advertisement's claim. Okay? All right, so let's start out with the claim. Okay? Let's see. HO is that it cures baldness. And HA is that doesn't cure baldness. And I like writing out HO and HA and really drilling down deep into what's what, so these things don't mess around with my mind. All right, so we got a type 1 error. If your father makes a type 1 error in his evaluation, which of the following will be true? Type 1 error is, again, reject HO when it's true. All right, so we're rejecting that it cures baldness when in fact it does. So the cure really works, the cure doesn't work. All right, so these are out. And I'm pretty sure that that'll be out too, but let's check these two, because at least we have the first part of it, that HO is true, that this thing cures baldness. but your father doesn't believe the claim and doesn't buy the medication. All right, let's check the other one. The cure really works and your father believes the claim and buys the medication. No, that's not it. All right. So the cure really works and you've rejected it, doesn't believe the claim, or your father rejected it, and he doesn't buy the medication. So that would be your correct answer. So that would take E off of here too, and that's out as well. All right, a type 2 error is where HO is false, but you accept it. So let's write that out. All right, so let's see. If HO is false, then this means it cures baldness is also false, so the cure doesn't work. So it's going to be either this one or this one. So those two are out. I'm just going to assume that one is out. So we're down to C and D. So the cure doesn't work, but your father believes the claim, he accepts it, and buys the medication. That's it. Right? The cure doesn't work and your father doesn't believe the claim and doesn't buy the medication. That doesn't make any sense. All right? Okay. Let's see what we've got for number 3. A one-sided hypothesis test is performed with a significance level of 0.05. Now remember, that's alpha. Suppose that the null hypothesis is false, right? If a significance level of 0.01 to be used instead of a significance level of 0.05, right, that's another alpha and it's smaller, just for reference. Let's see what we've got here. Neither the probability of a type 2 error nor the power of the test would change. Well, remember, if alpha gets smaller, beta should get bigger. So these are changing. That's out. Both the probability of a type 2 error and the power of a test would decrease. They cannot decrease at the same time because if a type 2 error goes down, then the power should go up. Let's try C. Probability of a type 2 error and the power of the test would increase. Nope, they can't do the same thing together. They have to be in opposition. All right, probability of a type 2 error would increase. Now that's looking good because when alpha goes down, beta, probability of a type 2 error, should go up. If the type 2 error goes up, then the power of the test should decrease. That is correct. All right. For just looking at the last one, the probability of a type 2 error would decrease and the power of the test would increase. Those are in opposition, but if alpha is decreasing, beta should increase. So that is out. All right. So I'm going to pause because I got to get to the next 2 problems. So hold on with me. So back at it. Number 4 will probably be the toughest one. What you might want to do is just take a moment, pause the video, read through it. I mean, if you didn't bring your own answers to the thing, maybe pause the video now and see the explanation afterwards and see if you pick the right one, because kids really have trouble with this one. All right, so a police officer uses a motion detector to indicate whether a car is traveling faster than the speed limit. A speeding ticket will be issued to the driver of the car if the officer believes the driver is speeding, as indicated by the detector. Situation is similar to using a null and alternative hypothesis to decide whether to issue a ticket. Hypotheses can be stated as follows. All right. HO, driver's not speeding. HA is that the driver is speeding. Okay. Let's see. It says, which of the following best describes the power of the test? All right. And remember, power is correctly rejecting a false HO. So power is correctly rejecting a false HO. So I guess the problem is say, assuming if it's going to be power of the test, that this is false. And we should be rejecting it, all right? So if we reject it, we should determine that the driver is speeding and give them a ticket. So which of the following best describes the power of a test? The probability of issuing a ticket to a driver who is speeding. That was exactly what I said, maybe in a slightly different order. All right? So if this is false, then we should correctly determine that this is true. And if it is true, then we should issue a ticket, or the policeman should. Or if we're the police, we should do it. Right? So write this out, do the reasoning, do a little doodling. It certainly can help. Here's the last one. All right. A medical doctor uses a diagnostic test to determine whether a patient has arthritis. Treatment will be prescribed only if the doctor thinks the patient has arthritis. The situation is similar to using, null and alternative hypothesis to prescribe the treatment. Here's the hypotheses. Either the patient doesn't have arthritis or they do. All right, a type 2 error. That's where your HO is false, but we accept. All right, so let's see what we've got here. All right. Diagnosing a patient, diagnosing arthritis in a patient who has arthritis. All right, well, let's see. Diagnosing arthritis, that's claiming that this is false in a patient who does have arthritis. Well, if we're saying this is false, but they actually do have arthritis, that's sounds like a type 2 error. All right. Let me pause this and make sure. Every so often I get a little bit wrapped around, so hold on. All right, I'm glad I took the pause because A can't be right? Because a type 2 error is that the patient does not have arthritis, but we believe they do. All right. Diagnosing a patient with arthritis when they have it, HO is that they don't have it, so that can't be right. That's saying like HO is that they do have it. All right. So let's check B. Failing to diagnose arthritis in a patient who has arthritis. All right. Again, this will be accepting HO when it's false. So let's see. Yeah, I'm going to check that one too. Hold on. All right, I'm back. Like I said, these can really blow your mind. You have to think long and hard about them. So, failing to diagnose, we're on B here. Failing to diagnose arthritis in a patient who has arthritis. HO is that they don't have arthritis. All right, so that can't be right either. So any of these that say they have arthritis, that can't be a good answer. So let's go ahead and cross those two off, and let's move on to C. All right, the patient does not have arthritis. So this looks good, this part of it, and we should make a mistake because if it were correct, we should diagnose that they do not have arthritis, but we're diagnosing that they do. That's the answer. All right, I think we have this nailed down. Let's try the other ones. I'm going to put myself out there and see if I can confuse myself any further. Failing to diagnose arthritis in a patient who does not have arthritis. All right, how can you fail to diagnose arthritis in a patient who does not have arthritis? That doesn't make any sense. Prescribing treatment to a patient regardless, that's out. That's just a dumb foil. So, HO is false, but we accept it. They do not have arthritis. We believe they do. So that's C. So finally, sorry, I had to stumble around a little bit with that one, but I had to come up with an instant answer on this, and these things take a little bit of time. So